Okay, let's do this radical review together. Radical numbers are numbers that have square roots in them. And so here we go. We're going to be adding them together. Radicals, when you're combining them, are a lot like variables. If I had a negative 9x plus an 8x, we would know that would be negative 1x. So same thing over here. If I have negative 9 square root of 7s and I add 8 square root of 7s, I'm going to have negative 1 square root of 7s. Here I've got square root of x plus square root of x. Same thing as if I had x plus x. How many square root of x's do I have? I have 2 of them. I've got 4 square roots of x, and I'm going to take away one of them. And so I've got 3 square root of x. I know some of these are going to seem basic, but at the same time, I know through past experience problems that students miss, so we're going over all of them just to make sure we've covered the bases. Here we've got multiplication, so we know that 3 times 2 is 6, then square root of x times square root of x. If you want to think about it, I mean, you don't have to think at all, but if you want to think, square root of x times square root of x is the same thing as square root of x squared, right? Because we have 2 of them. And the square and the square root cancel each other out, and that's why that's equal to x. We'll just have x. Another thing to notice, there are no pluses or minuses here. If you wanted to string this out without the parentheses, you could rewrite it as 3 times 2 times square root of x times square root of x. There's no distributing. There's just multiply the numbers together, multiply the radicals together, and that's how you get your answer. Here we've got square root of 20. You're saying, well, Miss Overby, we're done. We square root of 20, square root of 20. It's not a perfect square. And that's very true. Or you could say, Miss Overby, we could just put this into our calculator and get, what would we get, 4 point something? But that's not what I'm going to expect you to do. I'm going to expect you to be able to simplify something like square root of 20. And if you remember back in middle school, the way they taught this was to make a factor tree. So you could think of any 2 numbers you wanted that multiplied together to equal 20. Let's say 4 times 5. And we would stop after we would do that and say, are any of these prime numbers? Now remember, a prime number is a number with 2 factors, 1 and itself. So we look at 4. No, 4's got more than 2 factors, so we can break down 4. 4 can be broken down into 2 times 2, right? Is 2 a prime number? Yes. We're going to use that. We're going to use that. Is 5 a prime number? Yes, because 5's factors are 1 and 5. So what we do once we break down 20 into its prime factors, we put them back underneath the radical sign. What's underneath the radical sign is actually called the radicand. Not that you need to know that, but now when we do that, we remember that anything that occurs twice underneath the radical sign gets to come out. And why is that? Well, I could rewrite it like this, right? Would that make sense? That square root of 2 squared is 2, so the 2 gets to come out. That's why the 2 gets to come out and the 5 stays in. Okay. We could rewrite this. Now, once again, I'm trying to give you different ways to think about it. We could rewrite, since we had this, 2 times 2 times 5, we could rewrite it as this, square root of 2 times 2 times the square root of 5. That's the same thing. And once you do that, then you can see, oh, we've got 2 and then times square root of 5. Another way to do it could be skip the whole factor tree and see if you can come up with a perfect square that's hidden in 20. And sure, we know there's a perfect square hidden in 20. It's 4. Once you find the perfect square, you can, in your mind or on paper, you can rewrite it like this. Square root of 4 is 2, and then we have 2 square root of 5. I don't care which route you take, but I want you to know that it's not about just staring at it. You can either make a factor tree or find the hidden perfect square in there, and then get used to the fact that this is the same thing as this if we write it 2 different ways. Just get used to radical language. Radical math language. Okay, square root of 125. We can make a factor tree, or we could find the perfect square located in there. Is there a perfect square located in there? Absolutely. 25, right? So we'll have 25 times 5. I can rewrite that, though you don't need to do this step, but I am doing it so that you can see why my answer is 5 root 5. So this is when it says simplify. This is what it wants you to do. On the ACT, you're going to need to know how to simplify, as well as on this unit test. All right, now we're multiplying radicals, and of course the 5 and 4 are not radicals, but they're part of, each of them are part of a radical. So what we're going to do is we could rearrange this multiplication, because see how we see 5 root 6? That's the same thing as saying 5 times root 6. Just to give you an example, if we had 5x, would you agree that's the same thing as saying 5 times x? It is. All right, same thing here. The parentheses also mean times, and then we've got 4 times root 3. If you write it like this, then it would make sense to reorder it and say, well, we're going to multiply the whole numbers first, and then we'll multiply the radical numbers second. 5 times 4 is 20. 6 times 3 is 18, so it's 20 square root of 18. Are we done? No, we're not done. Square root of 18 can be simplified. Is there a hidden perfect square in there? There sure is. 9 is hidden in there. So we can go ahead and take square root of 18 and rewrite it. We can rewrite it as square root of 9 times 2, remembering that that's the same thing as this. And so square root of 9 is 3. So we know that another way to rewrite square root of 18 is 3 square root of 2. So then we have 20 times 3 square root of 2. This is still all multiplication. So 20 times 3 is 60. So far we have seen no distributive property. If you didn't want to go through all of this to get here, you could have just looked at it and said 5 times 4 is 20. Root 6 times root 3 is root 18. There you go. We already got all the way down to this step. I'm trying to show you as many different ways. I'm also speaking quickly and writing quickly, and that is to make this whole lesson as short as possible for those of you that really do remember Algebra 1 and Algebra 2, which is great. For those of you that really need this review, please stop and slow me down and pause and rewrite things and rewind, do all that stuff. Make this your own review, whether it's flying through it or rewinding it. All right, so let's look at 8 once again. This time we've got a couple options that we can do. I'm going to go ahead and simplify root 27x, and I'm going to say, oh, there's a hidden perfect square in there, right? 27 is 9 times 3. Now I could have done the factor tree. I'm just using the perfect square method because that's a little bit quicker. You get the same answer if you did the factor tree. So that's the same thing as saying square root of 9 times square root of 3x. Square root of 9 is 3, so I've got 3 root 3x. Okay, so I just rewrote square root of 27x. And then square root of 3, I can't do anything to. So now I'm going to look at this, and I've got 3 times root 3x times root 3x. And if we really want to see what that is, we have 2 ways to think about it. We can say that's 3 times square root of 3x squared, right? Because anything times itself is itself squared. And when we do that, we know that the square and the square root undo each other. And the 3x is free. So 3 times 3x is 9x. That's one way to get the answer. Another way to think about it, when we get to this spot right here, when we get to 3 times root 3x times root 3x, another way to think about it is this. I can put root 3x times root 3x underneath the same radical sign. I can put it as 3x times 3x. And when you think about that, you've got, I'm doing a tutorial. I am doing a video.
And so, must be something going on with teachers because I was already picked up.
Darn it.
By Gina Caruso.
Okay. All right. Thanks. That's okay. Thanks. Okay. So if we did this, then we're going to go ahead and multiply the 3's together, right? And multiply the x's together. And you would get 9x squared. And then you'd say, well, square root of 9 is 3. That gets to come out. Square root of x squared is x. That gets to come out. And that gives me 9x. Once again, lots of different ways to think about it. and do it. You've got to pick the way that makes sense to you because your brain is not going to remember something that does not make sense. All right, square root of 12x to the 7. All right, so what we're going to do is we're going to be looking for perfect squares, both with our number and with our variable. So when I'm looking at 12, I know there's a perfect square hidden in there, and that's a 4. And then, so that's 4 times 3. And then look at x to the 7th. And when we think of perfect squares, we normally think of 1, 4, 9, 16, 25, 36, right? But variables can be perfect squares too. What do you need to be to get out of a square root? You need to be something squared. For instance, 4 is 2 squared. So when I look at this x to the 7th, I could rewrite it like this, right? 1, 2, 3, 4, 5, 6, 7. Okay, I could think of it this way. I could go ahead and say, well, the 4 comes out because square root of 4 is 2, and then the 3 has to stay in, unfortunately. I'm going to rewrite it this way. And I could also think going back to the factor tree, every 2 things gets to come out. So x times x gets to come out once. X times x gets to come out another time. X times x gets to come out another time, and then there's an x left. So that gives me 2x cubed, square root of 3x. Now that's not normally, that's not the, I shouldn't say normal, but that's not the first method that most people will pick, but it is a method that you can understand, and if you understand it, you can do it that way. Another method could be to do the same thing. We could do the same thing and rewrite it as 4 times 3, and then we could think of x to the 7th as being x squared times x squared, so let's see, that's x to the 4th times another x. No, let's see, 2, 4, another x squared, then another x. And then when we look at it that way, any perfect square gets to come out of the radical. So square root of 4 is 2, square root of 3 has to stay in, x squared, the square root of x squared gets to come out, gets to come out, gets to come out, gets to stay in. That's another method, not usually the method that we use, but I'm just showing you all the methods. Here's the method that we're going to use. Did you notice how square root of x to the 7th, if we could just focus on that, square root of x to the 7th, what came out? X cubed, x cubed. And what was left inside? Plain old x. Plain old x. And the reason why is this. Since we have a square root, what we're forgetting is it's really like there's a 2 in there. We don't normally see that unless we're doing the cube root or the 4th root, but there really is a 2 in there. And so what we could do, a shortcut is to say, all right, we've got x to the 7th. How many times does 2 go into 7? It goes in 3 times with 1 left over. When you do that, that means that x to the 3rd will be what's on the outside of the radical, and your remainder, x to the 1st, will be on the inside of your radical sign, of the square root sign. So you can do that even if you have, let's say, and we're going to a different type of problem, but let's say you have the 5th root of x to the 12th. It's the same thing. You're going to say, how many times does 5 go into 12 evenly? It goes in 2. 2 times 5 is 10. How many do we have left over? 2. So that means, okay, it's a little strange. We both got 2s. But this 2 tells me that x to the 2nd gets to come out. And then what stays in? The 5th root of x squared. Okay. Hopefully that didn't confuse you more. All right, so now we've got same thing. We're going to multiply. There's a couple different ways we could do this. We could look for perfect. Did we finish that one, by the way? Let me look. Yeah, we finished it. Okay, so there's a couple different ways we could do this. We could just multiply everything together. Why don't we do it that way? A root times a root, a radical times a radical. I can put everything under the same radical. And I can say I've got what? 5 times 40 is 200, and then x times x to the 9th is x to the 10th, and then I can start pulling things out. I think for this problem, this is the fastest way to do it. So is there a perfect square hidden in 200? There certainly is, 100. Are there any perfect squares hidden in x to the 10th? Yes, so I could write x to the 10, or x squared, x squared, x squared, x squared. But I'm going to write it like this, and I'm going to do my shortcut. First of all, I'm going to pull out the 10, right? Square root of 100 is 10. And then what's left over is the 2. And I'm going to stop, and I'm going to say, okay, I have x to the 10th. How many times does 2 go into 10? Because square root is saying it's a second root. 2 goes into 10 and even 5 times. So out comes x to the 5th. Do I have any remainders after that? No, no remainders, so there's no x left in there. This is our answer. Once again, if you wanted to do it the long way, if you wanted to say, x to the 10th as x squared times x squared times x squared times x squared times x squared, you know every single square root, and we could rewrite this as what? Like this. Right? For those of you that ask really good conceptual questions, this is for you, to show you why we can do what we do. This and this mean the same thing, and it's really obvious. Square root of x squared. The square root and the square undo each other. It's just an x, just an x, just an x, just an x, just an x. What do we have left? X to the 5th. A lot of different ways to get the same answer, which is my point. All right, with 12, square root of 25x. All right, this is awesome. Square root of 25 is 5. Does that x get to come out? No, it stays in there, locked away forever. All right, it's the radicand. All right, this one says 5 square root of x squared, and I'm going to rewrite this like this so I can see the square. And I'm going to do this 2 different ways. One way is more the conceptual way that says if I have anything squared, it's basically saying, or not just basically, it is saying that you take what you have and you multiply it again by itself. Let's stop and do a. You multiply it again by itself, and then no distributing. It's just simply multiply the number times the number, which is 25, and the radical times the radical. Well, root x times root x is just x. And if you wonder why, I'll show you the long way again. Root x times root x, you can rewrite it like this. You can rewrite it like that. And see how the square root and the square cancel each other out? Yes, so it's 25x. So you can do it once again, I keep repeating myself, but I'm repeating myself so that for those of you that this doesn't come naturally to, there is a longer way that really does make sense. Do it. For those of you that the shortcuts make sense, do the shortcuts. Here's another way to look at the same problem. Just like if I had, let's say, xy squared, we would know that that would mean x squared y squared, right? We know that the power goes to both the x and y. So same thing here. If I have this squared, it's going to be 5 squared and square root of x squared. 5 squared is 25. The square root and the square cancel each other out, and this is the answer that we get. Okay, this is not the same thing as what we just saw. So we've got to be really careful. This square only goes to the square root. The 5 stands alone. The square root and the square cancel each other out, and the x comes out. So we get a different answer. Before we got the 25x. This time we get the 5x. If you need to slow it down, go backwards, stop and think about it, please do. The goal is not to rush through this. The goal is to use this to understand. Once again, this stuff appears on the ACT, and it will appear on our test, even though truly this is Algebra 1 and Algebra 2 topics. And I say that not to make anybody feel bad or not as a shaming thing. I say it because there's some things that are so important in Algebra 1 and Algebra 2 that we must take the time to review. We use them again and again, and it's worth reviewing. All right, so here we go. We've got the square root of x to the 6th squared. We see the square root. We see the square. those two things cancel each other out, just like addition cancels out subtraction when we're doing anything. And multiplication cancels out division, especially in solving equations. Square roots and squares cancel each other out, and you're just left with x to the 6th. All right. Here, for the first time, we see a plus. We see something besides multiplication. All right, we know this is a binomial, and since it's to the 2nd power, we're not going to use binomial expansion the way we learned it in Chapter 8. We're going to go ahead and do this by hand. We're going to rewrite it, since square means take what you have and multiply it by itself. That's what we're going to do. And we're going to remember to go ahead and distribute. Square root of x times square root of x is square root of x squared, which is x. By this time in the video, I want you to know square root of x times square root of x is x. Then we're going to distribute square root of x times square root of 7. Once again, square root of x times square root of 7, I can write as square root of 7x. So that's going to be plus square root of 7x. Then I'm going to move on to distributing my second term in the first binomial, square root of 7 times square root of x, same thing, we've got plus square root of 7x, and square root of 7 times square root of 7. Once again, you need to know square root of 7 times square root of 7 is 7. But why? Because square root of 7 times square root of 7 is the same thing as square root of 7 times 7, which is square root of 49, which is 7. All right, so we're going to pull this together, and we've got a very colorful problem. We've got x plus, okay, we've got a square root of 7x. We have another square root of 7x. How many do we have together? We have 2 of them. Can I combine any of these terms? No, they're all unlike terms, and we cannot combine them. That's as simple as we can get. Okay, here it says 7 root 5 plus square root of 125. This reminds me of remember way back when you might have seen like 7x plus 2, and you would have said 9x. No, right? Because we can't combine things that are not alike. So this appears to be something like this, maybe 7x plus y. It appears like we have 2 things that cannot be combined. So before we just go, that's it, we can't simplify it, let's look to see what we can do. If this problem right here was written as something times square root of 5, then we could combine it with 7 root 5. So what we're going to do is we're going to focus on square root of 125 first. We're going to ask ourselves, is there a perfect square hidden in there? Yes, 25. For those of you that are going to ask, how did you know? Well, I work with numbers a lot, but so do you. So think about, if you want to, maybe on the top of your page somewhere, or maybe you have a square, paper square of all the perfect squares to remind yourself, oh, 125, that looks like it has a 25 in it, right? 25 times 5. Okay, we know that 25 times 5 is the same thing as root 25 times 5. We know root 25 is 5, so there we go. We have 5 root 5. We got our wish. So because we can rewrite square root of 125 in terms that have a square root of 5, we can continue this problem. So we're going to rewrite it. We've got 7 root 5 plus 5 root 5s. How many root 5s do we have? We have 7 here, we have 5 there, we have 12 root 5s all together. Tricky, but fun. At least that's what I think. All right, oh my gosh, we got cube root. Okay, up till now we've just been doing square root. Once again, we usually write square root like that, but there's really a 2 in there. Okay, we just don't write it because that's just common knowledge that the square root, you don't have to write the 2. But when you do cube roots and fourth roots, you're going to start seeing the number right snug in there in the radical sign. And what that means is this. Can this number, instead of being written as a perfect square, can it be written as a perfect cube? So let's talk about what does that mean to be a perfect cube? Well, 1 is a perfect cube, right? Because 1 times 1 times 1 equals 1. How about 8, right? Because 2 times 2 times 2 equals 8, so 8 is a perfect cube. How about 27? Yep, that's a perfect cube. How about 69 or 64? Okay, that's where I'm stopping. No, we also know 5, right? 5 times 5 times 5, it's 125. That's where I'm stopping. Okay, so now we need to become flexible with our perfect cubes. And so because when we have a cube root, it's saying nobody gets to come out unless there are 3 of them. For instance, if we want to talk about cube roots without really doing this problem, if we had 3 x's here, they would come out because the rule is if there are 3 of the same things being multiplied underneath the cube root sign, they get to come out. That answer would be x. Another way to write this would be cube root of x cubed. You'll note just like the square root and the square cancel each other out, the cube root and the cube also cancel each other out. So that would be x. But let's go back to our problem. So here we go. We've got a negative, which is cool, right? Because we could also see that -1 is a perfect cube because -1 times -1 times -1 is -1. And -8 is a perfect cube, right? So negatives can be perfect cubes, while of course negatives can't be perfect squares. So here we go. -64, we know what that is. That's the same thing as -4 cubed. Since the cube root and the cube cancel each other out, -4 is our answer. 4th root of 32. Well, let's see. I'm going to do my work here. Let's see if we can write 4 2's. Let's see. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. In this case, 32 broke down into 5 2's. So think about it. Only 4 of them get to come out, right? Because I could rewrite this like this, which I could rewrite like this, which would be the 4th root and the 4th power cancel each other out. So I'd have 2, like this, and we'd have this. Okay, once again, I don't suggest that you do it the long way. I'm just trying to appeal to the logicalness in your brain. Your brain wants to know why. So once again, if we just go back up here and realize, well, we had an extra 2. So the 4 2's get to come out, but that poor remaining 2 has to stay inside underneath the 4th root sign. Okay, this next one, we've got the 3rd root. We know that 25, or 5 rather, we can rewrite 125 as 5 cubed. So that's going to get moved out. We know what to do with this x to the 7th. We're going to take 3 and we're going to divide it into 7. 3 goes into 7 2 times. That means that, well, let's see, as I'm going to put this here. We're going to pull out the 5, of course, and what's left inside. Let's see. We'll do a cube. Okay. This 2 means x squared gets to come out. And then we see what our remainder is. 2 times 3 is 6. And our remainder is 1. One of the x's has to stay in. Now, if you don't like that way, you can take your time and you can go through writing x to the 7th 7 times. This rule says anything that's being multiplied by itself 3 times may come out. So x times x times x, boom, can come out. X times x times x, boom, another one can come out. This poor x has to stay in. X times x is x squared, and that's how we got that. And that's how we got the x that stays there. As long as your brain can understand it and you can replicate it, you're good to go. All right, so now we're doing the 5th root. Let's go ahead and do the shortcut, and basically we're going to say we've got a 10, we've got a 5. How many times does 5 go into 10? It goes in 2. Am I going to have any remainders? No. That 0 means there's nobody that's going to be stuck in the underneath the radical sign. So we'll have x squared gets to come out, and then let's look at this 21. We're going to do 5 goes into 21, what, 4 times? That means that y to the 4th gets to come out. And then let's look at 5 times 4 is 20. What's the remainder? 1. One of the y's gets stuck behind underneath the 5th root. Once again, if you feel more comfortable writing out the 10 x's and 21 y's, you can do that and you'll get the same answer in a way that you can understand. All right, cube root. All right, before we tackle the cube root, we're going to simplify what's underneath here. So here we go. We have x to the 10th, y to the 5th. This reminds me of stuff that we did in our exponent review. So x to the 10th over x, that's going to be x to the 9th. Y to the 5th over y squared, that's going to be y cubed. And of course, you've already watched that video, so you have no questions about that. So now we're going to put that back under. So we'll have cube root of x to the 9th, y to the 3rd. How many times does 3 go into 9? It goes in 3. So x to the 3rd will come out. How many times does 3 go into 3? Once. And y comes out. This is your answer. Please feel free to slow down the video, pause, do things the long way to make sure you're getting the same answer that I am. Okay, let's do this as well. Let's break it down before we do the fourth root. So I'm going to take this out. Let's see, how am I going to break it down? 4 goes into 4 once, 4 goes into 120 30 times, and then we'll have what? X to the 4th on the bottom. The y to the 5ths cancel each other out. Now we're going to do the fourth power. Is there a fourth power hidden in 30? Let's see, 2 times 2 is 4 times 2 is 8 times 2 is 16. I think not. That poor 30 is going to be stuck underneath there, isn't there? But x to the 4th, x gets to come out, and we'll have the fourth root of 1 over 30. Once again, I realize I am speeding up the pace because I'm trying to get this done before my next class comes in. Please slow it down and pause it if you need it. Okay, 2 binomials being multiplied again. Here we go. Now we're distributing. This is only the second problem that we've had to distribute. So root 3 times root 8, we know that's root 24. Root 3 times 1, we know that's root 3. 5 times root 8 is just like 5 times x. 5x, in this case, it's 5 root 8. And then 5 times 1 is 5. Okay, it looks like a mess, right? It looks like we have nothing that we can combine. Let's look at this root 24. Do we have a perfect square stuck in there? We do. We have a 4. But you know what? Is that even going to help us? I think not. I don't know if we can't combine anything here, unfortunately. What a mess. We could break 24 down into root 4 times 6, so that'd be 2 root 6. But still, we don't have any of these terms that are alike. We cannot combine any of them. That was a very sad problem. All right, 27 to the 2/3. I can't remember if this was included in your exponent review or not, but basically when we have a fractional exponent, the top number is the power. So that's squared, cubed to the 4th power. The bottom number is the root. Cube root, square root, 4th root. So it's always advantageous to do the root first, especially if you have it. Do we have a cubed root hidden in 27? Well, let's think about it. 3 times 3 is 9. 9 times 3 is 27. So we do. So we're going to do that first. We're going to say the cubed root of 27 is 3. We're done with the root part, and all we have left, I meant to write a 2. All we have left is the square. So 3 squared is 9. Now, if you wanted to, you could square 27 and then take the cube root of that number and you would get 9, but not as easy to do, right? Especially without a calculator, which not sure if you can use a calculator on this part of the test. I don't think you can. So do the root first. All right, let's look at the next one. We're going to do the root first. This says the second root, which is square root. Square root of 25 is 5. What's remaining? The negative 3rd power. We know that negative means to flip the whole thing, so that's 1 over 5 to the 3rd, which 5 to the 3rd is 125, so that's 1 over 125. I think we're getting closer to the end. Oh my goodness, all these fractional exponents. So let's remind ourselves, when we multiply the same base with that have powers, we add the powers. In this case, it would be what? 5, 4, that would be 9. It would be x to the 9th power. So what we're looking at is we're looking at adding these powers. When we're multiplying the same base raised to powers, we are going to be adding them, only putting a minus because it's the same thing as plus a negative. So aren't we lucky we get to do some fractional addition? What's our common denominator? It will be 12. So let's see, if I multiply the bottom by 4 to make that 12, I have to multiply the top. If I multiply the bottom by 3 to make that 12, I multiply the top. If I multiply the bottom by 6 to get 12, I multiply the top. Hopefully I don't make a mistake going this fast. So 8 plus 3 is 9, 9 minus, no, 8 plus 3 is 9. 8 plus 3 is 11, 11 minus 6 is 5, so that's 5/12. So in this case, as I write down something else, so in this case, the hardest work was doing some fractional addition. So our answer is x to the 5/12. A little bit harder than our sample problem of just adding 2, 3, and 4. All right, are you going to have to know how to do that? Yes, yes, yes. All right, here we're being reminded, even if we have a fractional exponent, when we have power to a power, that means we multiply. Just like when we have x squared y cubed raised to the fourth power, that fourth power goes both to the 2 and to the 3, and power to power means multiply. Now, of course, that's not our problem, but I just wanted to remind you of the laws that we're using. So when I look at this, I've got fourth times negative 3 halves, and y to the 8th times negative 3 halves. And we have to remind ourselves about fractional multiplication. Basically, we're just multiplying straight across. 4 times negative 3 is negative 12. 1 times 2 is 2. You can reduce it, and that's a negative 6. So I'll have x to the negative 6. And then we'll have 8 times negative 3 over 2. Yes, I realize I can reduce before I multiply across, but I am just going to do it this way. So that's negative 12. So that'd be y to the negative 12. Is it good manners in math to leave exponents that are negative? No, it's like leaving your elbows on the table. So let's put them underneath the 1 and be done with this problem. All right, 29, do we just have 30? Yay, we just have 30. All right, power to power again. All right, here is something that's interesting. I'm going to give a more simple or a simpler or a, more simple was good. Let's say that's squared, and I'll make that into a 3. Okay. A lot of times it's really easy to forget that power goes to this too. So we would have 3 squared, we would have x to the 6th power, we'd have y to the 8th power. So that's our easy example. So here we go. We're going to have 8 to the 4/3. We're going to have x to the 6th times the 4/3. We're going to have y to the negative 1/2 times the 4/3. Once again, power to power, we are multiplying. 8 to the 4/3, remember we're going to do the root first. The cube root of 8 is 2. 2 to the 4th power, 2 times 2 is 4, times 2 is 8, times 2 is 16. Here we're going to multiply across. We're going to get what? 24 divided by 3, which is 8. So we'll get x to the 8th. Here we're going to multiply across. We'll get negative 4 over 6, which reduces to what? Negative 2/3. Yep, let's make it pretty. The 16x to the 8th stays on top, but that y raised to the negative power has to go into the denominator and becomes positive, of course. All right, one last one. Whew, all right, power to power, here we go. We'll have x to the 3 halves, we'll have y to the 3 halves, we'll have 1/4 times 4, which is 1, we'll have 1/4 times 8, which is 2, and now we've got same base raised, so I'm going to put a 1 there to remind. If I'm going to look, and I'll rewrite this so it makes sense to people. Once again, when we are multiplying a string of multiplication, we can move things around however we want. That's a really nice thing about that. So here we go. Same base. I'm going to add the power. So 3 halves plus 2 halves is 5 halves. Same base. I'm going to add the power. So 3/4 plus 8/4 is 11/4. And we are done. Woo! Awesome. Okay, I hope that was as fun for you as it was for me. My expectations are that you will be able to do any problem like these problems in this video. Thanks for joining me.